And so let's get into the good stuff here. So let's talk about model checking for a neural network. And so here's the setup. So we have a sequence of m variables over n time steps. So these are the positions in that vector that was used as an X notation in the earlier slides. And so what we divide this up into is we have a prefix and a suffix. And you can essentially think prefix is what you observe, and then the suffix is what gets produced by the model. So in your initial data set, you have both, of course, as you train the model, but that position I is where it breaks off. And so if you have a parameterized model, now here, the F symbol, unlike the earlier slides, is used to represent the output of your neural model. So notice your neural model is taking in input for each position, but up until time I, because it's only getting the prefix. And of course, we have a set of parameters theta, and the output, you get a bunch of X hats over time period I plus 1 through n. So the suffix for each position in that vector. So what we say, yeah, go ahead.
The previous slide, I couldn't exactly grasp what the X stands for. W superscript K equals X superscript K subscript 0.
So omega is, well, let me talk over here so we hear it right. So omega is used to represent the entire vector, and the X superscript K subscript the time period is a way to specify the time and the position of part of that vector. So the difference between the two is X is subscriptable by time as well. Yeah. All right, so we say that, hey, the entire sequence has to satisfy an STL formula. And that's what we're going to require. So what we want to find is we want to find a set of parameters theta that minimizes what they talk about as a distance to the ground truth, and also satisfies the specification, the STL specification. And they use L2 loss in the paper. So in the paper, they provide a series of example STL formulas that would be specification, and they put them in some different categories such as reasonable range, consecutive changes, and so forth. And if you go through these, you could kind of get a feel, sort of like that diagram I showed you in the part introducing STL. Is they're all kind of stuff like that, putting some sort of constraints on the signal. But now bear in mind, unlike that diagram, we're not just talking about a scalar value, we're talking about a vector. So we're putting constraints on all positions of the vector. Okay, so how do we go about doing this? So we have a student-teacher network paradigm. Now, there is a little bit of nuance in the figures that I'm going to show you in this paper. I actually went and looked at the reviews on OpenReview, and they're not really two neural networks. So I want to just kind of make that clear up front. So be ready for a little bit of a, I don't want to say misrepresentation, but I think like probably not the best way to communicate the algorithm, or best word to call it, because you have a student network is actually quite straightforward. So it's just a recurrent neural network or a transformer, and you're just taking all that data, and the prefixes is what's seen, the suffixes are your ground truth, and you're training a model to fit that using this L2 distance function. So very straightforward, no guarantees it's going to meet any kind of specification. The teacher network is not even really a network. It's taking the result of the student network and it's modifying it so it meets the specification. And then what they have is they have a specialized loss function that they use actually in the student network, that part of the loss function is to measure the loss based on the ground truth. And the other term in the loss function is to measure a distance to this recently created sequence that meets the specification. Okay. And so then it trains again. So what does that loss function look like? Well, you have this hyperparameter beta, and like that first part with the L between omega hat and omega, this is comparing the output sequences with the ground truth, where 1 minus beta is multiplied by a distance function that is comparing the output of the network to the teacher result, which is the modified sequence of the last thing. So how close is it to a sequence that is guaranteed to meet the spec? So what you got here is, since this goes iteratively, and how the student network assigns parameters is how much it values satisfying the constraints versus fitting the data is what beta is telling us. So the higher the beta, the more it fits the data and the less it's worried about the constraints. You have the teacher network that at any given iteration is giving you something that meets the specification, because it's going in there and it's sort of just messing with the result so it meets the specification with this extra refinement step. And then in the next iteration, it hands it off to the student network. Now the student network trains parameters that the idea is they're going to be closer to, meeting both requirements, fitting to the data and the specification. Now, this is kind of neat from an operational perspective, because never does the student network guarantee you it'll produce a result that meets the specification. The teacher network, that's essentially the student network plus this extra step, is always going to meet the specification, but it could have high loss. And so it's kind of a nice little balance there. And you could also maybe imagine a more sophisticated version of this that wouldn't be hard to extend, where maybe you have multiple specifications, some that might be hard and some that may be soft, and you could maybe have a third term because you could split out the specifications. There's nothing here that would prevent you from doing that. Yeah, question.
So if this is minimized, there still remains a chance that the student network at that point still does not meet all the specification constraints.
That is true. There's no guarantee the student network will ever meet the specifications.
But that's like what we are trying to optimize or work towards.
But yeah, so you could think of it this way. So the I'll call it the teacher refinement algorithm, because it's not network itself. It's just taking the results of the student network and it's just adjusting it so it makes sure it meets the spec. But because of this iterative process, the output of the student network is going to be closer to meeting the specification while simultaneously fitting to the data, even though you can't make that guarantee.
That's true.
Yeah.
But something like was previous days that example with the cyclist and the pedestrian, that for the safety constraint that it has to be, the network should always meet the specifications, and we should not allow it to not meet specifications.
So in that application, in the deployment of the model, you'd want that teacher refinement algorithm being implemented in that, because that would assure you that you'd always meet it. Now, the thing is, though, is because you would have trained the model in this paradigm, the teacher algorithm shouldn't have to mess with the results a whole lot because it's already going to be kind of close based on how it's trained. Yeah. Yes.
In the previous slide, I guess the fourth point is steps 2 and 3 are repeated iteratively. It should be 1, 2, and 3, right?
Yes, that is correct. Yes. Okay, so this is just what I just said. You got the two models and you're just going to keep iterating that until convergence and you get this really nice pair of results. And depending on your application, if those constraints need to be hard or you just need to get it to be close to the constraints, you pick which one as an engineer that you would use. And so throughout the rest of this is P will be the result of the student, Q will be the final result of the teacher. So here's the architectural overview, and this was the diagram I kind of didn't care for too much because it's showing the same network and it's making you think there's two neural networks. But again, if you pull up the reviews, a reviewer had that exact same comment, and then the author said, no, it's just doing this refinement. There's not a second network. So yeah, that's about how I reacted to it. Okay. Now, got some people in the waiting room. All right, so trace generation. So this is actually the teacher process here. And actually this I thought was kind of interesting how they went about doing this. What this highlights to me, and I'll talk about this a little bit later, is this notion of even if you have what's a black box model here that's producing the result, your black box model. If it's producing a symbolic result, you can do manipulations to it on the symbolic side that could be interesting and useful. And that's what's going on here. And if you notice, this idea has come up in a few different papers that we have seen. And what I think is really interesting about that is we've seen it come up in like some very disparate places, right? The inductive logic programming guys talked about it, but also the deep symbolic regression guys did it. And this is, I think, still different. Verification people are very different from those other two communities. So it's kind of interesting, this concept of refinement keeps cropping up by people who generally don't talk to each other. So, okay. So we can think of the result of the neural network as kind of like a sequence of worlds, because it's going to have, atomic propositions associated with that vector at each time. So this is a bit of they're quantizing the result of each time step of the neural network. So the idea is that if we can change the specification into a format where now we can just go world by world. So if we turn the specification essentially into a list of time points of everything that's true at each time point, then it's kind of easy, right? You can just go to each one and you see what's different and you just change the minimal amount of stuff. And that's basically what's going on here. So the first is to turn this into a disjunctive normal form. So the idea by doing this as a first step, putting it into disjunctive normal form, you get several options as to what you need to satisfy. And so, so right away, that's kind of taking a big chunk of complexity out of there. Then the disjunction is then a conjunction of literals. And those conjunctions are then really easy to compare with a given output at each time point of the neural net. And so once you can do that, that last step, like I said, is kind of trivial because you're just comparing at each time step, you're essentially comparing two sets of ground atoms. So this diagram I actually really liked. They started out with this initial formula and they convert it to a disjunctive normal form, which essentially is now being changed to 3 different formulas. And so then what they do is they look at, they can break it down, and they break it down into the 2 disjuncts, and they can see, hey, you know, the first one is requiring X to be greater than 1. The second is requiring X to be less than or equal to 0.5 or to 5, excuse me. And so right away, we can start to compare those values, as you see in the box on the lower right, as you look at it, and you can identify based on those formulas, which one the sequence produced by the RNN is closest to, and then you can take that adjustment. So, you know, the first key result is that you can do this, that you convert an arbitrary STL formula to disjunctive normal form. And, you know, they don't even list this as a theorem, they call it a proposition. It's actually, you know, fairly straightforward syntactic manipulation. And actually in the paper, they show an algorithm that handles this, and it does it iteratively, breaking it down as we go through. So for example, if it identifies a disjunction in the main formula, it already is going to separate those out, and then it's going to recursively apply itself to both sides until it bottoms out. Okay, so on that note, let's take a look at the experimental evaluation. And so metrics, they looked at root mean squared error and percentage of specification satisfied. And they also had this measure here where they looked at this distance to satisfaction. And then they showed how it could be in the appendix. They showed how it could be computed for different formulas. Basically, all you really need to know here is that when it's at 0, it's satisfied. You know, from the main point they're trying to get across in the paper is more about percentage of constraints satisfied. Distance to satisfaction, though, it is useful when you want to compare, like, say, a naive approach to the result of the student network, where you allow things to be violated. But as you'll see in the results, the percentage of constraints satisfied is also significantly less there too. And here they are. So this is on generated data, and they did this experiment with both LSTM and transformer. And we could see that with the P again is the student, Q is the teacher. You just kind of get that out of the way. And of course, the teacher, the distance to satisfaction is always 0, always satisfies everything with 100%. Root mean squared error actually is somewhat competitive with the other approaches, which is kind of a nice result. But when you think about it, it makes sense because you are still taking that, you know, very last result of the student network, and you're modifying that. So the refinement step isn't doing a whole lot of work because it should already be very close. And likewise, you see rather high satisfaction rates on the student network. And again, it's because of that loss function. They're directing it also toward a result that is able to satisfy the constraints. And of course, you get rather poor satisfaction rates, you know, with, you know, the baselines, which is hardly surprising because that's not, you know, considering that at all. They also did a real world investigation on, well, using real world data for air quality prediction. And they also, what was interesting here is they looked at different lengths of sequence and what happened to the results, as well as how it deals with missing data. And so again, here, of course, we get the STL, so the LSTM is, of course, by itself generally getting the lower error rates, although we do see, it's fairly competitive from the other two. Generally, it seems like it, at least according to this one experiment, it still remains competitive as the lengths get longer and as you reduce the amount of data. But this was kind of, one thing that some of the reviewers complained about is, this is actually still pretty limited. They didn't do any comparison with transformer architecture on this data set, and they never say why. And, again, this is the only real world data set that they tested on.